Okay, so next problem, relative motion problem. Those problems, they are not that straightforward. So here we have to deal with a plane motion. So this is the combination of translational and rotational motion. And those problems, like, they are sometimes quite tricky. You need to be careful with a whole bunch of different things. Okay, I always recommend to start with the links connected to the frame. Stationary frame, restricts the motion of those links, and we can extract a whole bunch of different important facts. Okay, for example here, right, so motion of point C. So we can see here the slot is not straight. That cross here tells us that this is the circle, so this is usual notation of the circle center. That means that motion of C is tangential. Velocity of C is perpendicular to this radius. Right, so let's maybe draw it here. I always try like to draw everything up to scale in these problems, because a good schematics is extremely important. A bad schematics can be misleading and actually can lead you to the wrong solution, or like some kind of unresolvable situations. Okay, here it is perpendicular, so if this is 5, 12, so the tangent here is defined by 5 and 12, so 5, 12, and this is 13. So then here, so since it is perpendicular, slope is going to be inverted. Very simple geometrical fact, right? So it's 5 and 12. So this is velocity C, and we know that it is 36 inches per second. So we know that it is downward, like, and perpendicular to this radius in this case, right? So you can see we from this link connected to the frame, so we extracted the direction of velocity C. Okay, so this is good. So then so since it's moving downward, right, so it's going to push B to the left, and since this roller is moving along this surface, velocity of B is going to be pointing to the left. And that again like gives us another direction of the vector, so which is velocity of point B. So as you can see, without much of an effort, we extracted quite valuable information. 2 directions, right, of different vectors. So also let's maybe right away extract another geometrical fact. As you can see, we have to calculate angular velocity of BC, right? And that means that we need to know length of BC, and we do not know the length of BC, but it is given like by this slope. It is 3, 4, and 5, right? And with this distance 60. So this is enough information like to actually calculate it, right? So let's maybe draw. This is going to be 60, right? And let's log this triangle. This is going to be our right triangle here. And let's maybe notate this angle theta. And this is also going to be theta, right? Okay, so from this slope, we can say that cosine of our angle theta is equal to 3 divided by 5. Okay, and from this triangle, it is 60 divided by BC. So our BC is equal to 60 multiplied by 5 divided by 3. 60 multiplied by 5 is 300. 300 divided by 3 is 100. 100 inches. Okay, good. So now let's write relative velocity equation for link BC. Velocity of B plus velocity of C relative to B is equal to velocity of C. So this is absolute velocity, this is relative velocity, and this is absolute velocity. Absolute means relative to Earth. Okay, and then velocity of C plus velocity of B relative to C, and this is equal to velocity of B. Okay, another important fact which we must know and apply, that those relative velocities, they are perpendicular to the link. Because if, let's say, we sit on point C, we do not feel motion of point C once it's moving downward, right? And this point B is going to be on the same distance all the time from point C, because link has the constant length. Okay, so that is why once we sit at point C and observe motion of point B, so which is going to be a relative motion of point B relative to C, we will see purely rotational motion. So velocity of B relative to C is going to be tangential, and it's going to be perpendicular to a link BC. Okay, so let's write it down here, and it's going to be same like if we sit on point B and observe point C. So we can write that relative velocity here, so this is velocity of C relative to B, is perpendicular to C, and velocity of B relative to C is also perpendicular to BC. Okay, so this is good. It doesn't matter what equation you use, you will get exact same triangle, so just kind of mirrored like around BC. I usually choose equation so which is easier to represent using the vector triangle on the link itself, right? So for example, if we look at this side from the side of C, picture is a little bit overcrowded, so that is why I would choose equation, so which is going to build the triangle from this side. And this is going to be this equation right there. We are going to solve it using a geometric approach. We are going to construct the vector triangle tip to tail rule, so applying tip to tail rule, and then we are going to resolve the triangle using sine and cosine law. So this approach is affordable to any student at high school. We are not going to apply vector algebra here, so just again like simple geometrical facts like and some fundamental rules of vector addition. Okay, here we have velocity C, we see velocity C, we know velocity B, so something like about velocity B, we know its direction, but we do not see this vector right there, right? So we do not see this vector right there, right? So that is why I usually recommend to rearrange this equation so we get this vector naturally, rather than like sitting and trying like to kind of fit it into the into this triangle as is. Okay, so this is velocity of B relative to C, and let's move C to the right, so this is going to be VB minus VC, or we can also write it that this is VB plus minus VC. Okay, minus VC is the same vector as VC, just flipped to the opposite direction, right? Okay, and we know that our relative velocity vector is perpendicular to BC. So let's maybe draw that a line perpendicular to BC. and then apply tip to tail rule, right? So then we will take this vector VC, flip it, and then apply tip to tail rule, right? So this is more or less perpendicular. So this is good. So let's draw this dashed line here. Somewhere there, our relative velocity vector will be located. Okay, so then we have minus VC, right? So minus VC. So let's maybe move this notation down. So this is our VB. Okay, and VC. We'll grab it, and it's going to be minus VC. So it's pointing in the opposite direction, right? So this here is minus VC. Okay, and then here this vector there is going to be our relative velocity vector. So as you can see, extremely straightforward, right? So extremely straightforward. So this is velocity of B relative to C. So that's it. So we have the triangle. Now we just need to define all the angles, right? Okay, so let's maybe redraw it. So let's maybe redraw it in a larger scale. I don't know, let's maybe try to select it somehow. Let's see if we can do something like this. So you don't need to redraw it. We'll just make it larger. Okay, so this is good. So this is our velocity B. This is our 36 inches per second. So this is our minus VC. Okay, and this is our velocity B relative to C. Okay, so this is 36. This is 512, right? So let's notate this angle as alpha. Okay, so then BC, so this B relative to C, it is perpendicular to link BC. Since link BC has the slope 3, 4, so this is going to have inverted slope of 4 and 3, right? And this angle, let's notate it as beta, and let's notate this angle is as gamma, right? So it's gamma. Okay, I recommend, like in this particular case, to actually convert angles to degrees. In some cases, it is possible to manipulate with just sine and cosine, but not always. So that is why I recommend, like in this particular case, to sacrifice a little bit with accuracy. So if you need like to convert like your sine and cosine back and forth to degrees, like, and like back like to slope, but it's going to be always like consistent way of calculations. Okay, let's see. So tangent alpha is equal to 12 over 5. So our angle alpha is equal to, let's see, 12 over 5 and our tangent 67.4. Right, so 67.4 degrees. Okay, so tangent of angle beta is equal to 3 over 4. So our beta is equal to 3 divided by 4. 36.9. 36.9 degrees. Okay, and gamma is just going to be 180 minus 67.4 minus 36. Okay, so let's see how much is that. So it's 180 minus 67.4 minus 36.9. 75.7. 75.7 degrees. Okay, so this is good. So we can maybe, let's write it here. So this is 67.4 degrees. This is 36.9 degrees. And this is 75.7 degrees. Okay, so we have a side, right, known. So this side is known, and we have two angles, right? So this is good. So our triangle is set. So we can calculate everything in this triangle using sine and cosine law. Okay, so what do we need? We need the angular velocity of BC. So we only need this relative velocity. So that's the only thing like we need. Okay, so let's use sine law. So we have velocity of B relative to C divided by sine of 67.4 degrees, right? And this is equal to 36 divided by sine of 36.9 degrees. As you can see, guys, like here we could actually like use sine and cosine defined by the slope. But again, like if let's say we also need the velocity of point B, absolute velocity of point B, so then we still need this angle gamma, right? So we still need this angle gamma, and we still need to convert like those slopes like into angles in degrees. So again, like whatever you like, but I just recommend, like in this particular case, yes, we a little bit sacrificed accuracy. As you can see, like what we are doing, right? So we converted like those slopes like into the angle, right? And then like we basically converted like backwards, right? So you can see here we are using sine. So this is a little bit of the accuracy loss, but just a little bit. Okay, so we have relative velocity. So this is equal to 36 multiplied by sine of 67.4 degrees divided by sine of 36.9 degrees. Okay, so let's see how much is this. So we have 36 multiplied 67.4 sine divided by 36.9. This is sine as well. Okay, so it's 55.4. That's a 55 0.4, and this is inches per second, right? So inches per second. Okay, so to calculate our omega angular velocity, you can see angular velocity here. So since tangential velocity b relative to c is pointing in this direction, so it's going to be clockwise motion, right? Okay, so omega bc multiplied by bc, so this is going to be our tangential velocity b relative to c. Okay, and our omega c is equal to relative velocity divided by bc, right? So this is 55.4 divided by 100, so which is equal to 0.554 radians per second clockwise. Okay. So that's it. So you can see it's not that bad. Like if you move step by step, first consider all those links connected to the frame, right? So set up those relative velocity equations, choose whatever equation you like, construct like this triangle. This rearrangement helps a lot to construct like that triangle. So once you have triangle, again, like usually it's a very straightforward geometrical problem.